right, so the main aim of this lesson is to give a very thorough introduction to the concepts of. We have seen earlier that Sn, which is the set of all bijections of a set containing n element onto itself, which endowed with function composition satisfy all of the following properties. The set is closed under function composition. The composition operation is associative. There exists a neutral element called the identity element. We've seen that Sn is closed under taking inverse. And we have also looked at seemingly different sets endowed with completely different operations. So for instance, we've seen that if we consider the following set of 6 matrices endowed with matrix multiplication, we've seen that all of the properties that you've seen we've discussed earlier are satisfied. In which sense, we have that this set is closed under matrix multiplication. Matrix multiplication is associative. Every element here has an inverse, which has 1 on the diagonal, is a neutral element. Now we will elevate this recurring phenomena to a concept, and this process is called abstraction. According to Frederick Goodman, abstraction is the process of elevating recurring phenomena to a concept, and it has several purposes and advantages. First, it is a tool for organizing our knowledge of phenomena. To understand phenomena, it already helps to classify them according to their common features. Second, abstraction yields efficiency by eliminating the need for redundant arguments, and certain results are valid for all groups and for all finite groups, or for all groups satisfying additional hypotheses. So instead of proving these results again and again for symmetric group, permutation group, groups of invertible matrices, and so on, we'll prove them once and for all groups. And this is a very appealing thought. Now let G be a set which we endow with an operation which we denote by star. And we'll assume that this structure, this pair, which consists of G and star, satisfying the following properties. So this is closure. G is closed under star. It is associative, meaning that if you have 3 elements that you're trying to combine through star, it doesn't matter whether you combine the first 2 first or the last 2 first. It doesn't matter how you associate elements. So this is associativity, and this property tells you that there exists an identity element. So there exists an element E in G such that for all X which is in G, X combined with E is going to be E combined with X, which is going to be X. So E is called the identity element or a neutral element. Every element has an inverse. So for every X which is in G, there exists an element which will often denote by X inverse, such that if you take X inverse is in G, such that if you combine X with its inverse, is the same thing as combining the inverse with X, and you get the identity. Alright, so whenever we have a set which is endowed with an operation star satisfying all of the conditions or axiom stated above, then we'll say that we have a group. It makes sense to look at some examples here, right? So let's G be the set of all integers, and let star be the usual addition. Now, the set of all integers is closed under addition, right? Because for every x and y, which are integers, if you take x plus y, you get another integer. So that tells you about the closure on the zero element is the identity. Indeed, given x, which is an integer, if you take x plus 0, this will be 0 plus x, and that will be x. Right, so 0 is the identity element. Every element has an inverse, meaning that if you let x be an integer, x plus the opposite of x is the opposite of x plus x, and that's going to be equal to 0. The structure Z endowed with addition, the usual addition here, satisfies all conditions required to be a group. Therefore, we'll say that this pair here is indeed a group. Now, here's a homework for you. I want you at home to verify that the set of all rational numbers, which is Q, which we denote by Q, which is the set of all fractions of the type m over n, where m and n are integers and n is non-zero. If you endow this set with the usual addition, so number addition, that gives you a structure of a group. So all you have to do here is prove closure, prove that the operation is associative, prove that every element has an quote-unquote inverse. Here the inverse here will be the opposite, and show that 0 is the identity element in this set. Okay, so I'll leave you with this homework. Now let us consider G, which is the set of all strictly positive real numbers. So by G, I mean the set of all real numbers such that x is strictly positive. You know, like 1 or 2 or half and so on. But 0 is, for instance, not an element of this set. Since the product of every two positive number is positive, then this set is closed under multiplication, right? So if you let x and y be two elements in G, since x is positive and y is strictly positive, then x times y is going to be positive. So this set is closed under product. We know that the usual multiplication is associative. So I'll let you verify this for yourself. All you have to show here is that, in fact, you don't have to show anything really. You just observe that for every x, y, and z, which is in G, x times y times z is going to be x times y times z. All right, that will show the associativity. Now, thirdly, the number 1 is the multiplicative identity. So indeed, given x, which is in G, x times 1 is 1 times x, and that's x. So we have an identity. If you let x be any element in the set, since x cannot be 0, 1 over x is also exists. 1 over x exists as a set, as an element, I mean. And moreover, since x is strictly positive, 1 over x is strictly positive, and that means that 1 over x is in our set. So every element has a multiplicative inverse. So we have all the ingredients required to have a group. This set is indeed a group. Now recall that I is the imaginary unit satisfying I square is -1. Let G be the set containing 1, I, -I, and -1, which will endow with the usual product of complex numbers, which we denote, multiplicative by the dots in the screen. Now, notice that if we look at this multiplication table, 1 times 1, 1 times I is I, -I, -1, I times I is -1, I times I is -1, and then you have a negative, so you have a 1, -I, I times I is -1, and then the -1 turns into a 1. I squared is going to be -1. This is going to be I, -1, I, and then 1, right? So you can see here that for every x and y in G, x times y is also in G. So this shows closure under complex multiplication. Now, you can see also that every element has indeed an inverse, right? And the way to see it is to go here and look at what we have. So 1 is its own inverse. Why? Because 1 times 1 is 1, right? What about I? What do you multiply by I to get 1? Well, if you look at the table here, look at these two, see that I times -I is 1. And if you look at -I times I, you also see that it is 1. Therefore, of I is -I. What about -1? -1 times -1 is 1. Therefore, -1 is its own inverse. So every element in this set has an inverse. Okay, so the set is closed under taking inverse. And complex multiplication is associative. Let's take this for granted. This set endowed with complex number multiplication has the structure of a group. So that's another example of a group. All right, so now let us recall De Moivre's theorem, which tells us that EI theta consists of all elements of the type cosine of theta plus I sine of theta, where I is the imaginary unit satisfy I squared is equal to -1. So De Moivre's theorem will allow us to give us tool that we can use to compute to come up with very interesting other type of groups. So let G be the set of all elements of the type E2 pi I k over 6, where k is either 0, 1, 2, 3, 4, or 5. It can't be 6. So there are exactly 6 elements in this set. Now, using De Moivre's theorem, you can check here that E2 pi I over 6 times 0 is going to be EI 0, right? But what is EI 0? That's cosine of 0 plus I sine of 0. This will be 0, so we get cosine of 0, which is 1. You can also check that E2 pi I over 6 is equal to this. Again, you simply use the fact that this will be cosine of 2 pi 6 plus I sine of 2 pi over 6, and then you use trigonometry to get the rest. this will be e2 pi I over e2 pi I2 over 6 is going to be this complex number. You can check here that this will be -1. Why? Because cosine of what is 2 pi 3 over 6 is going to be, if you take 2 pi times 3 over 6, that will be 6 pi over 6, right? So that's pi. So you get here cosine of pi plus I sine of pi. So that will be cosine of pi, which is 1, plus I times 0, which is -1, which is -1. And e2 pi I times 4 over 6 is going to be -half minus I square root of 3 over 2. And finally, we get this element. So there we have a total of 6 elements in G. And we hope to prove that this is in fact a group when we endow this with complex number multiplication. Okay, so suppose you let x and y be 2 elements of the group. Then you can rewrite x as being e2 pi I k over 6 and y as being 2 pi I l over 6, where k and l are sitting in between 0 and 6. Right? So now let's look at this product here. If we look at this product, we can rewrite this as e2 pi I 6 k plus l. Right? And then to show the closure of, to show that x times y is in fact an element of G, let's apply Euclid's algorithm to k plus l. So if you take k plus l and you divide that by 6, we have q as a quotient and we have r as our remainder. And clearly the remainder has to be in between 0 and 6. It has to be strictly smaller than 6. So what we'll do next is we'll take xy and we write xy as 2 pi I over 6, and k plus l is now 6q plus r. And the point is that this will be 2 pi I over 6 times 6q times e2 pi I over 6 times r. So this will be e2 pi I 6, 6q, those two will cancel each other out, times e2 pi I over 6 times r. And you can check that this will be 1 using De Moivre's theorem. So this will give you e2 pi I 6r, where r is in between 0 and 6. And so this shows that this is indeed an element of G. Okay? All right. Again, so going again through the calculations, we have this, and then we take this product, we look at e2 pi I 6q over 6, that's e2 pi I. De Moivre's theorem tells us that that'll be 1. So rewriting again xy as 1 times e2 pi I r over 6, since r is in between 0 and 6, then xy is an element of G. So G is closed under our operation. Now 1 is an element of G and is acting as the identity. Why? Because if you multiply any element by 1, you get 1. And how do you know that 1 is an element of the set? You just look at e2 pi I. You set k to be 0 over 6. That will be 1. Right? So 1 is in G. And that's our neutral element, because for every element in the set G, x times 1 is going to be 1 times x, and that will be x. Now to show that every element has an inverse, if you pick an element x in G, we can write x as e2 pi I k over 6 for some k in between 0 and 6. And notice that if you take e2 pi I k over 6 times e2 pi I negative k over 6, this will give you e2 pi I over 6 k minus k, but k minus k is 0, so this will be e2 pi I over 6 times 0, which is 1. And similarly, if you have e 2 pi I over 6 times negative k times e 2 pi I k over 6, this will be e 2 pi I 6 negative k plus k, right, which is e 2 pi I 6 times 0, and that's 1. Now, what we want to show here is that to conclude that G is closed under inverse, we have to show that this element is in fact an element of G. We write negative k as 6q plus r using Euclid's algorithm, where r is our remainders. Now, substituting negative k for 6q plus r gives us e 2 pi I r over 6. And that clearly is an element of G, right? Because G consists of all elements of the type E2 pi, which by definition, G is all elements of the type 2 pi I over 6k, where k is in between 0 and 6, not 6. So that tells you that E negative 2 pi I negative k over 6 is an element of G. And we conclude that this set is closed under inverse. So since complex number since the product of complex number is an associative operation, then all 4 axioms are satisfied, and then we can conclude that this set endowed with complex number multiplication is indeed a group. Now let us consider the following group, the set of all order pairs of the type XA, where X and A are real numbers, but A is strictly positive. Then we'll endow this set with the following operation, which we denote by star. And let us prove, first I will leave as a homework that this operation is associative. So check this at home. Pause the video and check this for yourself. Now, let us verify that G is closed under the given operation. So to this end, if we let XA be an element of G, and let's say YB is an element of G, then if you take XA star YB, so the operation tells us that X, this will be X plus A times Y, A times B, right? And the fact that since X plus AY is a real number, and the second component, AB, is positive, strictly positive, since A and B is strictly positive, it follows that G is closed under the operation star. Now, I want to show here that the 0, 1 is the identity. Indeed, if you take XA, say 0, 1 here, then by the definition of the operation, this will be X plus A times 0, A times 1, and this will be XA. Okay, and if we switch this around, we'll have 0 plus 1 times X, and then the second component will be 1 times A. 0 plus 1 times X is X. The second component, 1 times A, is A. Right? So for any element, for every XA in G, XA combined with 0, 1 is 0, 1 combined with XA, and that's the order pair XA. So the element 0, 1 is an identity. Now, I claim that every element has an inverse, and the way to see this is let XA be an element in G. Next, let's say little g be the element negative x over a and 1 over a. Since a is assumed to be strictly positive because xa is in G, then 1 over a is going to be strictly positive, and as a result, G is, of course, an element of the set, right? So now, if you take xa and then you combine it with negative xa 1a, what we get is x plus a times negative x over a times 1 over a. And this will be x minus x and a over a. So this gives us the identity element, 0, 1, right? On the other hand, if we take negative xa and 1a and we combine it with xa, we'll have negative xa plus 1a times x, and then you have 1a times a, and so this will be negative x over a plus x over a, and then a over a, and clearly this is 0, 1, right? So this tells us that every element, so G is in fact the inverse of XA. So we verify this. Every element has an inverse because of these two operations that we verify. Okay. Now here's another example. Let's, when we write GLNR here, this is the set of all invertible matrices. So it will be the set of all matrices such that M is of order n, is a square matrix, of order n, and the determinant of M is non-zero. Right? Because remember, a matrix is invertible if and only if its determinant is non-zero. So we endow this with matrix multiplication. So our operation here, star, will be matrix multiplication, and this will be G. And I claim that this is indeed a group, and so maybe the way to see it is to look at a simpler example first. Take M to be the set of all matrices of the type A, B, C, D, and notice that the determinant of M here is going to be, you take your product of the diagonal, so that'll be AB minus this, BC. So we're assuming that this is non-zero. Now, if you given M and N, so given M and N, which are two by two invertible matrices, the determinant of the product Mn, remember that the determinant of a product of two matrices is the product of their determinant. And since the determinant of M is non-zero and the determinant of N is non-zero, it follows that the determinant of M times N is non-zero, and consequently Mn must be an element. The product of Mn is an invertible 2 by 2 matrix. Okay, so this, we get closure under matrix multiplication. GL2R is closed under matrix multiplication. All right. Now, one can verify that the diagonal matrix with 1, 1 on the diagonal is the identity. So if I were you, I'll pause the video and verify this for yourself. And every element has an inverse. So indeed, if you take, if you let A, B, C, D be an element of the general linear group, the inverse of this matrix is can be computed as the following matrix with these entries. And to show that this matrix is invertible, all you have to do is in fact compute the determinant of this matrix and see that the determinant of this matrix is actually non-zero. And one way to do, in fact, so verify at home. So your homework here is to check that the determinant of A, B, C, D inverse is 1 over A, D minus BC. And since AD minus BC is non-zero, because the matrix is invertible, it follows that 1 over AD minus BC is non-zero, and consequently ABCD, the inverse of this, is an invertible matrix, so it belongs to the set GL2R, and this gives you thus GL2R is closed under taking inverses. Okay, all right. And so, in fact, you can check also that for every M, which is in the general linear group, you can check that M times M inverse is the identity 1, 1, 0, 0, and M inverse times M is also the identity 1, 1, 0. So every element has an inverse, as expected. So then we will see that this, in fact, so GL2R is indeed endowed with matrix multiplication is indeed a group. All right, next, let's consider the set R endowed with matrix multiplication. I claim that this is not a group, and to see it, so the proof is more or less clear. Let 0 be a real number. Since 0 has no multiplicative inverse, it follows that R together with multiplication, which I'll denote by dot, is does not have the structure of a group. Does not have the structure of a group. Now my challenge for you is to try to justify in fully satisfactory manner that 1 over 0 is not a real number. So can you explain why 1 over 0 is not a real number? Okay, try that. Now let's Z4. 4 here is a sub-index. So Z4 is the set of 4 elements, 0, 1, 2, and then 3. And then we'll endow this with an operation which we'll denote by plus star. And this is also called addition modulo 4. And let me explain what this addition is doing. So to add two numbers, x plus y, we'll say that x plus y, whatever this is, call it r, is the remainder obtained by dividing x plus y where this x plus y is in the usual sense of integer addition. So when we divide x plus y by 4, the remainder, whatever that is r. Okay? And we claim that this is an associative operation, actually. Now, if we look at the multiplication table here, you can see that, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, and so on. For example, 1 plus 1 is 1, 1 plus 3 is 0. Why? 1 plus 3 is going to be 0. Why? Because if you take 1 plus 3 in the usual sense, you get 4. But if you divide 4 by 4, you have a remainder of 0. You see? What about 3 times 3? Let's look at this. 3 times 3. If you take, so 3 plus 3, 3 plus 3. In the usual sense, 3 plus 3 is 6. But if you divide 6 by 4, you have a remainder of 2. So in this fancy addition, 3 plus 3 is actually 2. And so on. Again, pause the video and try to make sure that all of these entries that we obtain here make sense for you. And then try to verify that all 4 axioms required to be a group are present. And so Z4 endowed with this operation is a group. And we'll call this, in fact, a modular group. Okay, well, let's see. Now, here's some definitions. Suppose you have a group G endowed with some operation star. If G has finitely many elements, so that means that there's only a finite number of elements in the set G, then the number of elements in the set is called the order of the group. And we'll write that G is the order. This notation stands for the order of G. So simply the order of G simply is just the cardinality of G when G is finite. If G has infinitely many elements, we will simply write that the order of G is infinite. Okay? So for instance, if you take this group here containing 1i, negative 1, endowed with the usual product of complex numbers, which we denote by star, then the order of G is 4, right? Because you have 1, 2, 3, 4 elements in the set. If we have G, which is a group endowed with the star operation, we say that G is abelian or commutative if the following holds true. For any xy which is in G, x star y is the same as y star x. So in other words, it really doesn't matter the order in which you are combining elements. Take, for example, the general linear group consisting of invertible matrices of order 2. I claim that this is not an abelian group. Take these two elements. First of all, to verify that these two elements are indeed in the general linear group, it is enough to see that the determinant of 1, 1, 0, 1 is 1, which is of course not 0, and the determinant of 2, so the point that I'm making here is the following. Since the determinant of 1, 1, 0, 1 is 1 and is not 0, and the determinant of 2, 0, 0, 1 is 2, which is not 0, then 1, 1, 0, 1 and 2, 0, 0, 1 are element of the general linear group. Okay? Now, notice that if you take the first element, the second element, multiply by the first, we get the matrix with entry 2, 2, 0, 1. If we swap the order, so we take the first, now time the second, we get 2, 1, 0, 1, right? And those two numbers are not the same. Those two matrices, I mean, aren't the same. And the fact that they aren't the same tells you that the product 2, 0, 0, 1, 1, 1, 0, 1 is not the same as the product 1, 1, 0, 1 times 2, 0, 0, 1. So the general linear group is not a commutative or an abelian group. Or abelian group. On the other hand, if you take, for instance, a set of all real numbers endowed with the usual addition, then it's known that for any xy, which is a real number, x plus y in the usual sense is y plus x. Therefore, R endowed with addition is an abelian or commutative group. So in this group, order doesn't really matter. The way in which you combine elements, the order doesn't matter in the process. Now be careful. Not every operation is associative. You can check very quickly that x minus y, first minus z, is not the same as x minus, in parentheses, y minus z. Why? Because x minus y minus z is in fact x minus y plus z, which is very different from x minus y minus z, generally, right? So generally, those two things aren't going to be the same. So it's not true that every operation is associative. So instead of writing, for instance, x star y, we may write just xy, okay? And when we're denoting x inverse, we can just write, when we're talking about the inverse of x, we'll just write x inverse. And when we're talking about the identity, we'll just write E, or sometimes we'll just write 1 when it's clear whether what the operation is. You have to be very careful though, because the 1 written here has nothing to do with the 1 that we know of in the usual sense of real numbers. Okay? And so when we adapt this notation, this shortcut notation, we'll say that the operation, in this case, the operation or the group operation is denoted multiplicatively. Okay? So, and we can also denote our operation additively when it's clear what the operation is. So instead of writing x star y, we'll write x plus y. And in writing the inverse of x, we'll write just this. And in writing the identity, we can use the shortcut 0. And again, you have to be very careful because x plus y here has nothing to do with the usual addition that we're aware of. And this negative x that you see here has nothing to do with the opposite, because x and y may actually not be real numbers. There could be matrices. There could just be objects which we have attached no particular meaning to. Okay? And the 0 you know of, in the sense that we may not be dealing with real numbers. And when we adopt this notation, we'll say that the product or the group operation is denoted additively. If we have x combined with x, let's say n time, we can just write this additively as nx. If we have the inverse of x combined with the inverse of x combined with the inverse of x n times, we can just write additively negative nx. Again, one needs to be careful because the meaning here may not have anything to do with the usual meaning of nx or negative nx. We can also play the same game multiplicatively. When you have x combined with x n time, we can just write this multiplicatively as x power n. We have the same for the inverse, x inverse combined with x inverse combined with x inverse n time. We can just write this as x negative n. Again, be very careful because this may not have anything to do with the usual x power n when we are dealing with real numbers, because x may not even be a real number. Okay? When we adopt this notation, then we'll say that we are writing the group operation, or we're denoting the group operation multiplicatively. Now, at this point of the lecture, having been exposed to, in a pretty thorough way, to the concepts of what a group is, now it's time to test yourself. So can you pause the video and try to write down an example not given in this lecture? Come up with your own example of a set endowed with an operation, which is a group. And play the same game the other way around. Try to find an example, again, not given in this lecture, of a set endowed with an operation, which is not a group. If you can do that, then you have truly absorbed this new concept that you're being exposed to.